So, this is the second lecture. Do you have any questions from what we covered yesterday? Okay, so yesterday we just looked at the basic Maxwell's equations and also looked at plane wave solutions. And we found the relationship between the intensity and the electric field and showed the relationship between the direction of k vector, E vector, H vector and so on. So, today what we will primarily look at is anisotropic media, but before that let us recall a bit of diffraction. Although we will not be using too much of diffraction in the course, but I think we should be aware, because remember yesterday we had seen that the intensity is proportional to the square of the electric field. So, intensity we had shown yesterday is I is equal to n by 2 c mu 0 mod E 0 square. The nonlinear effects depend on the strength of electric field. The stronger the electric field, the stronger are the nonlinear effects. So, to increase the effects of nonlinearity, you have to increase the electric field, which means increase intensity. So, for a given power, you can increase the intensity by focusing the beam more, because intensity is power per unit area. So, if you take a certain power and focus it to a smaller cross section, you can increase the intensity and hence increase the electric field. So, if you focus a laser beam into a medium, you can increase the electric fields and hence the intensity and hence the nonlinear effects. But the problem is, if you try to focus a beam, then it will not maintain the cross section for a long distance, and that is controlled by diffraction effects. So, for example, if you take where does diffraction come in? So, if I take a slit and send a plane wave into the slit, the beam actually comes out and diffracts like this. This angle is approximately lambda by d, the width of the slit. So, this angle lambda by d is called the angle of diffraction. The smaller the value of d, the larger is the angle of diffraction. So, it is kind of an uncertainty principle between the width of the beam and the angle of diffraction. If you try to reduce the width, the beam reacts by diverging more. So, if you take a beam, for example, so how do you increase the intensity? You can focus it by a lens. So, I take a lens and I do a focus of the beam by a certain focal length lens. So, I take a certain focal length lens, this must be the approximately the focal length here, and it gets focused. So, if I want to reduce the cross section of the beam, I will take a lens of a smaller focal length. So, if I take a lens which is a smaller focal length lens, then you can see that this focuses like this and defocuses very quickly. This cross section, if you want to maintain a certain cross section over a long distance, diffraction plays a role here and does not allow you to keep the same cross section for a long distance. If you try to reduce the cross section, you pay a price by increasing the divergence. So, as an example, let me look at a Gaussian beam, which is the intensity distribution that is coming out of a laser is usually a Gaussian distribution. So, let me look at a Gaussian beam. So, the electric field of a Gaussian beam is some amplitude exponential minus x square plus y square by w 0 square. So, if you plot the electric field as a function of distance, something like this, and this is a here. So, this is a function of x, and the distance at which it becomes a by e is w 0 here. This value w 0 is the distance from the axis where the amplitude of the electric field decreases by a factor of 1 by e. And because intensity is proportional to square of electric field, at a distance w0 from the axis, the intensity goes down by a factor of 1 by e square. So, this w0 is called the spot size of the Gaussian beam. So, typically in a laser, when the laser beam comes out, w0 is of the order of 1 millimeter, half a millimeter, 1 millimeter. So, the beam comes out, and then this electric field actually is at one plane. So, let me call this at z is equal to 0. This electric field does not maintain itself forever. The same x and y distribution will not maintain itself because of diffraction. So, we will not study diffraction in detail, but let me tell you here, let me just give you the formula which gives me how the intensity varies with distance as the beam propagates. So, the intensity distribution of this Gaussian beam is given by I0 exponential minus twice x square plus y square by w0 square, where I0 is the intensity on the axis. At x is equal to 0, y is equal to 0, the exponential factor is 1 and the intensity is I0. And at x square plus y square is equal to w0 square, the intensity falls down by a factor of 1 by e square. So, this is at z is equal to 0. As you, so this is the Gaussian beam. So, let me plot here. So, this is the Gaussian beam at z is equal to 0 here. So, this is z is equal to 0 here. As the beam propagates, it expands like this. So, here for example, the Gaussian beam will become like this. Here it is slightly smaller, here it is even bigger. The Gaussian beam keeps on expanding as it propagates, and this is called diffraction divergence. So, if this is w0 here, suppose this plane I call z and this distance is w of z, then there is a relationship between wz and w0, which is obtained by analyzing diffraction. So, let me give you the expression here. So, w of z, w square of z is equal to w0 square into 1 plus lambda square z square by pi square w0 4. The width of the Gaussian beam, the spot size of the Gaussian beam increases with z according to this formula. Lambda is the wavelength of light in the medium in which the beam is propagating, and z is the distance at which you are measuring the spot size. For large z, for z much greater than pi w0 square by lambda, the second quantity in the bracket becomes much more than 1, and w of z can be approximated as lambda z by pi w0. I can neglect 1 in comparison to lambda square z square by pi square w0 4, and w of z becomes lambda z by pi w0. So, the spot size increases linearly with z for large distances. For small distances, the spot size does not increase linearly with z. It's a formula which is 1 plus lambda square z square by pi square w0 4. This is why I plotted here. It starts almost like this and then starts to expand, and then in the what is called as the far field, in the Fraunhofer region, the spot size increases linearly with z. So, I can define the angle of diffraction here is equal to w of z by z, which is equal to lambda by pi w0. It's of the order of wavelength divided by the size of the Gaussian beam, the spot size. Lambda by d is a very approximate formula depending on the shape of the beam. If it is Gaussian, it is lambda by pi w0. If you take a circular aperture, it is 1.22 lambda by the diameter of the circular aperture, and so on. So, these factors come in because of more precise estimations, but the angle of diffraction is approximately lambda by the width of the beam. So, you see this particular expression tells me that, so let me calculate what is the distance at which the spot size becomes root 2 times the input. So, at z is equal to 0, for example, your W of z is W 0. So, at z is equal to pi W 0 square by lambda, what will be the value of W z? So, this factor becomes 1. So, that is root 2 times W 0. So, the spot size will increase by a factor of root 2 in this distance, and let me put a subscript here. This is called the Rayleigh range. The distance from the plane z is equal to 0, at which the spot size increases by a factor of root 2. Please note here that z is equal to 0 is special, because that is this position where W of z is minimum. For z positive and negative, the spot size is more. So, this z is equal to 0 plane is also called as the waist of the Gaussian beam. So, usually in a laser, the waist of the Gaussian beam could be inside the laser, at the mirror, or outside the laser, depending on the laser construction. The waist of the Gaussian beam could be inside the laser cavity, on the mirror, on one of the mirrors of the cavity, or outside the mirror, outside the laser. But depending on the W 0 value, so W 0 is the spot size at z is equal to 0, which is the minimum spot size called the waist of the Gaussian beam. So, this tells me, so this is the distance over which your spot size will increase by a factor of root 2. Smaller the W 0, smaller is the Rayleigh range. So, if you try to restrict the beam to small diameter, you will diffract much faster. So, for example, if you take a wavelength of 1 micron, lambda is equal to 1 micrometer. So, let me take W 0 is equal to 0.1 millimeter, which is 100 microns. So, ZR comes out to be pi into 10 to the power 4 micrometers, which is pi centimeter. So, if you start from the from z is equal to 0 over a distance of pi centimeters, which is about 3.1 centimeters, the spot size becomes root 2 times larger than at the axis. If you reduce W 0 to 0.01 millimeter, which is 10 micrometers, because you have decreased W 0 by a factor of 10, ZR will get reduced by a factor of 100. So, ZR becomes pi by 100 centimeters. So, you cannot have a 10 micron beam over a large distance, because by the distance of pi by 100 centimeters, the beam has increased its cross section, the diameter, by root 2 factor. So, when you try to focus a beam to increase the intensity, you have to be conscious of the fact that that intensity is not maintained over a long distance, the beam will diverge very quickly. So, there is a relationship between the distance over which you can maintain the cross sectional dimension of a beam approximately to within a certain cross section and the cross section area itself. So, it is not always that you can increase the focusing to increase the intensity in electric field, but then you will lose in terms of how much length you can keep that intensity alive. So, many times what happens is people use waveguides to maintain a cross section over long distances, because in a waveguide, like an optical fiber, there is no diffraction. You have total internal reflection, which is not allowing the beam to diffract, and the cross section can be maintained over very long distances. So, for nonlinear interactions also people work with waveguides. These are waveguides with small lengths, a few 5 centimeters or 10 centimeters, and the cross sectional area could be as small as a few micrometers square. Diffraction will not play any role there, because the wave is guided by total reflection, and so the beam cross section does not change at all over the entire length. So, you can have much more increased nonlinear effects if you maintain the cross section over longer distances, and that is achievable in the form of waveguides. So, there are a number of people who work on waveguides to have strong nonlinear interactions, especially in optical fibers, for example. You can have very strong interactions. In fact, the nonlinear effects in optical fibers restrict the overall communication link that you have, how much of communication you can achieve. So, diffraction will play a significant role in all optics experiments and techniques, and one has to be conscious of this fact whenever we design experiments or when we look at numbers. I cannot assume I have an area of a diameter of 10 microns and take a length of interaction of 5 centimeters. It is not possible unless I have a waveguide, unless I know that I can restrict this. If I have a free space propagation, if I have homogeneous medium, I cannot maintain this. So, that I have to be a little conscious of. In fact, what I called as uncertainty relationship between the angle of diffraction and the width of the beam is kind of a Fourier transform relationship. It is a Fourier transform relationship. The angle of diffraction, the divergence and the width here are Fourier transform pairs. Just like you have frequency and time, if you have a short pulse, you have a large spectrum. If you have a long pulse, you can have a short spectrum. Similarly, if you have a narrow beam, you will have a large angle diffraction. If you have a wide beam, you can have small angle of diffraction. You cannot beat this. So, this diffraction is present in all systems, in all situations, and whenever we design experiments or when we think of numbers, we need to be aware of this concept. So, I would not go much beyond this in diffraction because we will not discuss more of details of this, but as I was mentioning, we need to be conscious of this. So, we will not touch upon diffraction anymore, except that when we look at the intensity levels in nonlinear effects, we will at that time bring back diffraction at that time. Okay. So, now what I want to start is essentially a discussion on anisotropic media. Okay. Now, as we will see, some of the nonlinear effects require certain conditions for efficient interactions, and those conditions require us to use media which are anisotropic. Now, what is the meaning of anisotropic medium? You see, yesterday we wrote this equation, D is equal to epsilon E, and I said that epsilon is a scalar. So, this means that no matter which direction I apply an electric field, the D vector is parallel to the electric field. Now, in crystals, in many crystals, this does not happen. If I apply an electric field like this, the displacement vector could be different orientation, and that comes in because remember D is nothing but epsilon 0 E plus P, polarization. And what is polarization? Polarization is the dipole moment per unit volume. So, when an electric field is applied to an atom, there is a displacement of positive and negative charge centers that makes dipoles, and usually the dipole is oriented along the direction of the electric field. But if the structure is not symmetric, you may apply an electric field like this and the dipole gets generated in some other orientation, because it has restoring forces from all directions which may not be all symmetric. So, in that case what will happen is P is no more in the direction of the electric field, and such media are called anisotropic. So, P and E are in general not parallel in these media. So, this depends on the crystal structure, and there are many crystal structures in which this will happen. There are crystal structures in which this does not happen because of symmetry, but a majority of crystals possess anisotropic. So, in general, which means that suppose I take a medium and apply an electric field which is along the x direction, suppose this is x cap E x, what you will find is you will find a finite dx, a finite dy and a finite dz in general. So, let me put a constant here epsilon x x E x, epsilon y x E x, epsilon z x E x. So, these are 3 constants. So, I apply an electric field along a direction x, some arbitrary direction which I call x, and I get displacement vectors along all 3 directions. That means, the displacement vector has all 3 components dx, dy and dz. Similarly, if I apply along the y direction, I will have another 3 components dx, dy, dz, and along the z direction. So, in general I can write, if I have a general electric field, I can have epsilon x x E x plus epsilon x y E y plus epsilon x z E z. So, this is the contribution to dx from E x, contribution to dx from E y, contribution to dx from E z. Similarly, dy will have epsilon y x E x plus epsilon y y E y plus epsilon y z E z, and dz is equal to epsilon z x E x plus epsilon z y E y plus epsilon z z E z. So, these equations tell me that if I have some arbitrary coordinate system x y z, I apply an electric field which has components E x, E y and E z. This electric field can in general generate all 3 components of a displacement vector dx, dy, dz. All of them depend on all the 3 components of the electric field. So, in fact, I can write this in a matrix form. This will become dx, dy, dz is equal to epsilon x x, epsilon x y, epsilon x z, epsilon y x, epsilon y y, epsilon y z, epsilon z x, epsilon z y, epsilon z z into E x, E y, E z. In a matrix form, this is the same 3 equations. So, in fact, I can write this as this is a D vector is equal to epsilon into E vector, where epsilon is now this 3 by 3 matrix. This column vector is the D vector, this column vector is the E vector, and that is the epsilon tensor. So, in component form, this is actually d I is equal to sigma j epsilon I j E j. So, here I and j take values 1, 2 and 3. So, many times this is simply written as epsilon I j E j, assuming that repeated indices are summed over. Okay. So, this epsilon is the permittivity tensor. It has in general 9 components. Now, one can show through arguments of energy conservation that this epsilon tensor will be symmetric. It is a symmetric tensor. So, you will have epsilon x y is equal to epsilon y x, epsilon x z is equal to epsilon z x, and epsilon x y z is equal to epsilon z y. So, there are only actually 6 elements in the epsilon matrix. So, that is a symmetric matrix. So, this matrix is symmetric, but in general all elements are non-zero. Now, it is possible to rotate the coordinate system in such a fashion that this epsilon matrix becomes diagonal. You can always diagonalize this matrix and you will get in one coordinate system which is called the principal axis system of the medium, in which the epsilon matrix becomes symmetric. So, I will have epsilon x x 0 0, epsilon y y 0 0 0, epsilon z z. So, this is called the principal axis system. The xyz principal axis, the xyz coordinate system in which epsilon is diagonal, is called the principal axis system, and these orientations of x, y and z depend on the symmetries of the crystal. So, if I know the crystal with its symmetry properties, I can find out which are the 3 principal axis directions of the crystal. So, these are 3 special directions in the crystal. So, if I write epsilon matrix in that coordinate system where x, y, z correspond to the principal axis, then epsilon is diagonal. If I use any other coordinate system, I will generate off diagonal elements. Just like you have transformation properties of vectors from one coordinate system to another coordinate system, you also have transformation properties of tensors from one coordinate system to another coordinate system. If epsilon matrix is this in one x, y, z coordinate system, if I rotate by an angle theta about the z axis, what will be the new epsilon matrix in the new coordinate system? I can calculate from here. Okay, there are some transformation relationships which tell me what the new epsilon should be. So, in most discussions, we will always be using the principal axis system because that is the easiest system to employ unless otherwise stated. If I find an epsilon which is not diagonal, then I know that I am not using the principal axis system there. I have to now rotate and find out that principal axis system in which my epsilon matrix becomes diagonal. But most of the time in the course we will be always using this principal axis system, and all quantities given in literature in terms of the epsilon values or nonlinear coefficient values, they are all in the principal axis system. Okay. Now, I can have 3 situations. I can have a situation when epsilon x x is equal to epsilon y y is equal to epsilon z z. In this case, this epsilon tensor becomes epsilon times the unit tensor. And then if you go back and look at the equations, it becomes a scalar essentially. The equation becomes d is equal to epsilon e and epsilon becomes a scalar. So, this corresponds to an isotropic medium. If the 3 elements principal, so these are called the principal dielectric permittivities. If all the 3 principal dielectric permittivities are equal, it is called isotropic. If 2 of them are equal and it is not equal to the third one, this is called uniaxial. If all 3 are unequal, this is called biaxial. So, these 2 are anisotropic. So, if all the 3 elements are equal, it is isotropic. If 2 of the elements are equal, it becomes uniaxial. If all the 3 elements are unequal, it is called biaxial. And by convention, the 2 equal components are kept as epsilon x x and y y. That is by convention. So, the 2 equal components will correspond to x and y, and the third one is the z one, and similarly for the biaxial, all 3 elements are unequal. So, most materials like glass is isotropic. You can have materials like lithium niobate, quartz crystal, these are all uniaxial, and there are elements like mica. Mica is a biaxial medium. It has all 3 elements are unequal. So, these anisotropic crystals provide us with additional degrees of freedom to achieve efficient nonlinear interactions, as we will see, as we will go through, we will see. So, what we want to do is to understand how light propagates in this media. What is the velocity of this wave? I have now in fact three quantities here. So let me redefine now here. So I can define now, because I am going to use the principal axis system, let me just write epsilon x, epsilon y and epsilon z instead of epsilon x x, y y, z z. Okay? And but these are, please remember, these are not the x y z components of a vector. These are three elements of the tensor, the three diagonal elements. I can define dielectric constants as epsilon x by epsilon 0, k y is equal to epsilon y by epsilon 0 and k z as epsilon z by epsilon 0. These are called the three principal dielectric constants. Three principal dielectric permittivities, three principal dielectric constants, and nx is equal to square root of kx, ny is equal to square root of ky, and nz is equal to square root of kz, the three principal refractive indices, permittivities, dielectric constants, and three principal refractive indices. So in isotropic, all three are equal. In uniaxial, two of them are equal, the x and y parts, and then the for biaxial, all three are unequal. So what we want to understand is, suppose I send a light beam through a medium which has three principal indices nx, ny, and nz. What is the velocity of the light, of that light beam, and does it maintain its polarization state as it propagates? Does it change its polarization state? What happens? How do I analyze this? So as all such phenomena are contained in Maxwell's equations. Maxwell's equations describe all electromagnetic phenomena. So what we need to do is to analyze Maxwell's equations with, under this condition, that D is equal to epsilon E. I am just drawing a double line on top of epsilon to remind you that it is a tensor, it is not a scalar. So in media in which D and E are not parallel in general, I would like to understand how light propagates. Now please note, there is one special thing about the principal axis. What will happen if I apply an electric field along one of the principal axis? Let me go back to this equation. So if I apply an electric field along the y direction, which happens to be the principal axis, what happens? So Ey is finite, Ex and Ez are 0, and it is principal axis. So what is dx?
Only in the y direction.
D will be only in the y direction, because remember, in the principal axis system, these are all 0. The off diagonal elements are all 0. So you will have dx is equal to epsilon xx Ex, dy is equal to epsilon y Ey, dz is epsilon zz Ez. So if I apply an electric field along Ey, dx and dz are 0, only dy survives. So principal axis directions are three special directions in which, if you apply an electric field, displacement vector is parallel to it. Yes, Mohit.
Are all the principal axes necessarily perpendicular to each other? I mean, the symmetry properties, they can be such that three axes that guarantee the of diagonal components to be 0 may be not exactly perpendicular to each other.
No. So the question is, are all the three principal axis directions always perpendicular to each other? Yes, they are always perpendicular to each other, because you will always find a coordinate system which is a orthogonal coordinate system in which your epsilon matrix becomes diagonal. So it is a orthogonal system, and so these are three special directions, and we must remember this. So if I apply an electric field along x, I will only generate dx, and similarly for the y and z. If you apply an electric field along any other direction, you will generate in general all three components, dx, dy, dz. Okay.
How did we get the expression for nx equal to root kx?
Okay. This is, I am just extending the concept of refractive index. I define the principal dielectric constant as epsilon x by epsilon 0, and I define the principal refractive index as this. Now this does not mean, I have still not told you where this refractive index will play a role as far as the velocity is concerned. I will have to find that out. So I will relate the velocity of the light wave in the medium to nx, ny, and nz. Okay, so I have defined three principal refractive indices, three principal dielectric constants, three principal dielectric permittivities. Okay, so I will now analyze the problem and I will obtain the velocity of the wave in terms of nx, ny, and nz. Okay, so we will continue to use this equation B is equal to mu naught h. Okay, so we will assume the medium to be non-magnetic. So B is equal to mu naught h. So let me write the Maxwell's equations again. So del cross E, the two Maxwell's equations, del cross E is minus del B by del T is equal to minus mu naught del H by del T, and del cross H is equal to del D by del T. Okay, now I want to look for solutions of plane wave solutions. How will a plane wave propagate in such a medium? So let me substitute a solution of this type. E is equal to E naught e to the power I k dot r minus omega t. A monochromatic wave, a plane wave propagating along some direction defined by k vector and having an electric field E naught vector. The corresponding H vector will be some H naught e to the power I k dot r minus omega t. Now, you see, when I substitute solutions of this type, I am looking for one special class of solutions called eigenmodes. I assume E naught vector and H naught vector to be independent of x, y, z, which means as the wave propagates, I want the polarization state not to change. I am looking for special solutions called the eigenmodes of the propagation, which are such that as the wave propagates, as the plane wave propagates, E naught vector remains fixed. It does not change with as it propagates. So, which means state of polarization does not change. Yes.
All these matrices are homogeneous.
Yes, yes. We are assuming that all media are homogeneous. I have only introduced anisotropy, so there is the medium is homogeneous and linear. Because of this equation, there is linear and it is homogeneous, which means that all the components epsilon x, epsilon y, epsilon z, they are all independent of x, y, z. Yeah.
Now that we have three different refractive indices, what is the magnitude of k?
Now that we have three refractive indices, what is the magnitude of k? We will find that out. We have to write, for example, k vector is equal to omega by c into some refractive index n. I have to find this out, because n will define the velocity of the wave. C by n will give me the velocity, phase velocity of that wave. I do not know the value of n. How n is related to nx, ny, and nz, I will find out. Okay, so I know the principal refractive indices, but I do not know yet how the speed of the wave will be determined by the three principal refractive indices. So that is my problem. So my k is still undefined in terms of n. I know it is omega by c into some refractive index, because the phase velocity is given by c by the refractive index, and I still do not know the value of n. I will find it out as a solution to my problem. So the problem which I have is I do not know the value of n, and I do not know what should be the direction of E naught vector, which will satisfy the condition that this will be a mode of propagation. This is a very important point. It is like when you look at oscillations of a string fixed at two ends, you first look for modes. You look for modes of oscillation. Similarly, because you can analyze any problem of oscillation of a string as a superposition of the modes. Modes form a complete set of solutions. Similarly here, I am looking for modes, that I am looking for the polarization states which will propagate unchanged and as a plane wave, because I am assuming E naught and H naught to be independent of x, y, and z. Okay, so let me substitute this into the two curl equations. So please remember that because of this, because of the form of this here, I will have del cross becomes I k cross. Wherever you get del cross, it will just become I k cross because of the space dependence of this form, and del by del t will get replaced by minus I omega. Del dot would have got replaced by I k dot, okay, because of the form exponential I k dot r minus omega t. So, the first equation becomes k cross E is equal to I omega, sorry, I k cross E I omega mu naught h, which tells me k cross E is equal to omega mu naught h. Second equation becomes I k cross h is equal to minus I omega d. This implies k cross h is equal to minus omega d. Yeah.
Could you explain the intuition by which we are saying that these eigenmodes will form a complete set, or we can define all other propagation modes using these eigenmodes?
Okay, this is something like an eigenvalue problem. Now, what we will find is, we will find two independent polarization states which will propagate unchanged for any given direction of propagation. And I know that any other polarization state will be written as a superposition of these two components, these two polarization states. There are, because this wave is a transverse electromagnetic wave, there are only two independent solutions for any propagation direction. I do not know whether the two independent solutions are linearly polarized solutions or circularly polarized solutions or elliptically polarized solutions, right. So, in Faraday effect, I will find that the two linear eigenmodes, the two eigenmodes are circularly polarized, which means when you have a right circular will remain a right circular, a left circular remains left circular as it propagates. Here a linear will remain linear, another linear will remain linear, but which linear? There are so many infinite number. So, I have to find out. So, if I give you an isotropic crystal and I say I propagate like this in some direction with respect to principal axis, which polarization should I choose here so that it propagates unchanged? I am trying to find the solution, and what polarization and with what velocity, with what speed will it propagate. So, all this is related to the principal axis system and nx, ny and nz, and because of its transverse nature, we know that there are two independent eigenmodes I will get. I do not know what polarization states are those eigenmodes, yes, yet. Okay, so let me put this back here. Now, please remember, D and E are in general not parallel. So, let me take a direction of propagation. So, this is k. So, I am not plotting the x, y, z axis here, it is some arbitrary direction of propagation k vector. The second equation tells me D is perpendicular to k. So, let me draw a D here. The second equation also tells me H is perpendicular to D, and H is also perpendicular to k from the first equation. So, it has to be out of this plane. K cross H is minus D. So, I am just plotting the H vector towards me. So, k is perpendicular to D from here, H is perpendicular to D from here, and H is also perpendicular to k from the first equation, and now D and E are parallel to each other, and E is also perpendicular to H from the first equation. So, E must lie in this plane, and in general it will not be parallel to D. So, let me draw a E vector like this. I do not know whether it is on this side or that side, I just draw some general E vector, and pointing vector E cross H will be like this now. this angle will be equal to this angle. So, in general, the Poynting vector and the propagation vector are not parallel, because D and E are not parallel. So, let me show you a slide which is an interesting slide which shows you this. Okay, so here is the figure which shows the respective directions of k, d, e and s, and the red lines which I am plotting there are actually the phase fronts, wave fronts. K vector is always perpendicular to wave front, because by definition k dot r is constant on the phase front. So, the phase front is like this. So, k vector is like this, but is propagating like this. The direction. So, if I had a beam like this, if I had a finite cross section beam, it will go like this. It will be facing straight, but it will move at an angle. So, that is what I am trying to draw here. S vector shows me the direction of propagation of the energy. The lines, the red lines are not perpendicular to S vector, they are perpendicular to k vector. And I found a nice picture here of acoustic waves in an anisotropic medium. The anisotropy is in acoustic anisotropy, not optical anisotropy. And you can see here it is a photograph taken of the wave fronts which are those lines, and the beam is propagating at an angle, exactly the way I have drawn in the figure. So, it is a beam which starts like this. It is a finite beam. It does not go like this, it goes like this at an angle. So, this is very characteristic of anisotropic medium, that the direction of propagation of the energy and the direction of propagation of the wave front are not parallel to each other, they are at an angle. We will get to know these numbers of this angle. This angle is not very large, it is a few degrees usually, but it is finite, it is not 0. And it plays a role in many interactions, because the energy plays its own role in terms of conversion efficiencies. The k vector plays its role in terms of in the efficiency, and so this is important. This knowledge that this k and s are not parallel is important to know. Now, can you tell me is there any direction in which if I direct k vector, s vector will also be in the same direction? What should be the k vector direction so that s vector is parallel to k vector? Is it possible in an isotropic medium?
Yeah.
Which direction?
If E is in the direction of one of the principal axes.
But only k is in my control. What direction should I propagate? K should be one of the principal axes. For example, if I choose k along x, and if the polarization D is along y, because D is perpendicular to k. So, if I choose my k to be along x and D to be along y, E will be along y, because D is along principal axis, and if E is along y, S is parallel to k. So, if I propagate in any one of the principal axis directions, the k vector and s vector become parallel to each other. Now, there is this classification which I told you, we will see. This uniaxial, the name comes from the fact that in media which have this property, there is one special direction. Okay, so I will come to this later. Okay, so in general k and s are not parallel, and so let me try to find out. So, this from these two equations I have got this fact that k and d are perpendicular to each other, E and s are perpendicular to each other, k and s are in general not parallel, and similarly E and d are in general not parallel. So, what is our problem? Our problem now is to find out what is the, from these equations, I need to solve this equation to find out what is the velocity of propagation of the wave and what is that direction of polarization that I must choose so that it remains unchanged. Now, let me tell you that because D is perpendicular to k vector, in anisotropic media the polarization state is defined by the D vector and not by the E vector. So, if I say linearly polarized along certain direction, it is the direction of D vector, because then it defines the direction of k vector. So, T vector defines the orientation of the polarization rather than the E vector in the in anisotropic media. In isotropic media it does not matter. So, D vector represents polarization state, and in general E and D are not parallel to each other. So, we will what we will do in the next class is to solve these two equations, simplify these two equations and find out what is the direction of this E0, what should I take, what is the E0 direction that I will have to choose. If I give you a propagation direction, what should be the E0 vector direction and what will be the corresponding value of n. So, this n will give me the eigenvalue and E0 vector will give me the eigenvector. It's just a kind of an eigenvalue problem, and so we will just start from these two equations in the next class and get the solutions. Okay, so do you have any questions?
Could you explain again, if I send the wave
Yes.
in the direction of one of the principal axes,
Yeah.
the D can be anywhere in the perpendicular plane. So do I need to I need to ensure that the other D is also along one of the other principal axes?
Yes, yes. No. Okay. Let me tell you this. If I choose one principal axis direction, I will show that the eigenmodes are D vectors along the other two principal axis directions. Okay. So, if I choose my direction of propagation along x, the D vector along y will propagate as unchanged, D vector along z will propagate unchanged, but the velocities of these two waves will be different. So, if I choose this eigenmode, then S vector is parallel to k vector. If I choose this eigenmode, S vector is parallel to k vector. If I choose any other state, it has to be written as a superposition of these two, but in both cases S vector is parallel to k vector. The only difference would be the velocities of these two waves are different. So, there will be a phase change, there will be a phase difference accumulated, but the S vector still will be parallel to k vector. If you choose a D vector like this, it has to be written as component this and component this. This component travels with a certain speed, this component travels with a certain speed, but both components have their S vectors parallel to k vector and the energy propagates in the same direction. So, whenever you propagate along any one of the principal axes, the energy propagation direction is parallel to the k vector direction.